one of the really neat things about linear programming problems is they can be visualized quite well. And I like to start off with an intuitive example where we can sort of build on and see the result of an important theorem that's going to allow us to figure out how to properly and efficiently optimize problems. Now, just as a quick reminder, recall that an LP problem, or a linear programming problem from our last video, is one in which you are either trying to maximize or minimize some objective function. In our previous case, that was to maximize revenue. In general, whatever function we're trying to maximize or minimize, we call that the objective function. And we have some subject to, and then we have inequality constraints. Could be one, it could be more. So we'll just say that it's possible that we'll likely have more than one. And remember, by inequalities, we're only considering the non-strict inequalities, meaning it has to be less than or equal to, or greater than or equal to. We can't have strict inequalities like less than or greater than, because then it creates sort of this line that we cannot pick points along, but we can get infinitesimally close to that line. So let's look at a flight plan. Suppose that we're looking at a commercial airliner. They begin to offer two new flights, one that goes from Phoenix to Las Vegas and another that goes from Phoenix to San Diego. Although they are excited to make their announcement, it is difficult for them to pinpoint exactly how many flights to allow each day. After all, they don't want to offer too many flights and have unfilled planes, and similarly, they don't want to offer too few and become less preferred to some other airline by potential passengers. So here's some information we have. So we have these two flights that we're going to consider, Phoenix to Las Vegas, Phoenix to San Diego. We get some information. They can offer no more than 8 flights to Las Vegas due to legal restrictions and costly tax scenarios. We don't need details, we just need to know that that's the case. They can offer no more than 10 daily flights to San Diego due to heavy air traffic. Okay, so no more than 8 flights to Las Vegas, no more than 10 flights to San Diego. And the fact that we're saying no more than means really less than or equal to 8 to Las Vegas and less than or equal to 10 to San Diego. An average flight to Las Vegas will yield $115 per passenger, while a flight to San Diego will yield $95 per passenger. A standard Boeing 737-300 can seat 137 passengers. Assume that each seat is filled. So we're not going to deal with the uncertainty of filling flights. The company's goal is to maximize its revenue. For each scenario, write out the restrictions and constraints as an inequality. Okay, so we're going to need some variables here. So we know this is going to be a linear programming problem because we're trying to maximize revenue, and our constraints are going to be linear in this process. So we want to know, what should the company do to maximize its revenue given what we've considered so far, these 2 bullet points? And we need some variables. We need a couple of variables here. So let's define, maybe we'll define we'll define X to be the number of flights that we're going to send to Las Vegas. We also need to know how many flights are we going to send to San Diego. So we'll define that to be Y for easy reference. And here we're given a couple of constraints, and so we're going to write those out. They can offer no more than 8 daily flights to Las Vegas. So that means whatever X is, the number of flights that we do send to Las Vegas, X has to be less than or equal to 8. That's a constraint. We can't just pick any values we want for X and Y because X has to be less than or equal to 8. They can offer no more than 10 daily flights to San Diego. Doesn't matter why, but that tells us that Y has to be less than or equal to 10. An average flight to Las Vegas will yield $115 per passenger, while a flight to San Diego will yield $95 per passenger. Great, so we want to maximize revenue, so we can start writing our objective function. So what do we want to do? We want to maximize this function, this revenue function. It doesn't matter what name we give it. I'll just use capital R though. And how do we calculate the revenue? Well, the revenue is $115 per passenger per flight, but we can seat 137 passengers. So first of all, we want to figure out how much we're going to make on each flight. This is just per passenger. So if it's $115 per one passenger, and we multiply that by 137 passengers because we're assuming we fill the flight, 115 times 137 suggests that we're going to get $15,755 in revenue from flights to Las Vegas. For San Diego, similar notion, would be $95 per passenger multiplied by 137 passengers, and it will be at 95 times 137 gives me $13,015. So our revenue for each flight, remember X is the number of flights, this is how much we're going to make per flight to Las Vegas, and this is how much we're going to make per flight to San Diego. So we're going to offer X flights to Las Vegas. This is how much we'll make on each flight. So we have to multiply the revenue per flight by the number of flights, and the revenue per flight to San Diego times the number of flights we're going to send there, which at this point we just know is going to be Y, some unknown. But we can't just make up, we could pick arbitrarily large values for X and Y and continue to make our revenue bigger. However, we're subject to two constraints. X has to be less than or equal to 8, and Y has to be greater than or equal to 10. By the way, in linear programming problems, there are always two assumptions, two assumed constraints, which I think intuitively makes sense since we are usually dealing with real-world scenarios here. X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. So in other words, we're only going to consider quadrant 1. We're only going to consider quadrant 1. No other quadrants will make sense. And the methodology we're going to propose here depends on the fact that we are working in the first quadrant. So this is kind of like a little sidebar here. This is always going to be true for these linear programming problems we look at. And we want to know, okay, so what should we do? Well, if we think about the fact that just because you offer, I think I wrote the wrong sign here. This should be less than or equal to 10, not greater than or equal to 10. The number of flights that I send to Las Vegas is not going to affect the number of flights that I can send to San Diego, because the only constraints that I have right now, I'm not seeing past what I'm being given, is that if I send all 8 flights to Las Vegas, I can still send all 10 flights to San Diego. So I think intuitively it makes sense that we should say, well, send all the planes that you can to Las Vegas and then send all the planes that you can to San Diego, because every time I increase X by 1, I'm going to make $15,755 more dollars, and same thing kind of goes for Y. So let's consider the ordered pair 8, 10. 8 flights to Las Vegas, 10 flights to San Diego. That's going to give me a revenue of $15,755 times 8 plus $13,015 times 10. And let's quick compute that using our calculating device. And so we get $256,190 in revenue. So I'm going to argue that's the most that we could possibly make. That the only other options are to make these guys go down. We can't make them go up. And even if I make one go down, that has no influence on the other because the constraints did not cross over and affect each other. So if I make either of these variables any lower, we're going to get a smaller revenue. So I think we can argue intuitively that 810 is the best that we can possibly do to maximize the revenue in this case. But let's go over to Desmos and let's go ahead and visualize this. So I'm going to just plot x less than or equal to 8. Now there we go. That's a vertical line, and the shaded region suggests points that satisfy all the points in this light green region satisfy where x is smaller than or equal to 8. We're equal to 8 along the vertical line. Even this point right here, for example, would be 4, 4, and the point 4, 4 is definitely has an x value less than or equal to 8. Now we're only focused on that first quadrant. You can see we get all this shading over here, but these linear programming problems are just limited to this. So right now I can pick anything inside of this green region. You might say, well, at this point you should just make y as large as possible, but we also have that constraint on y. We can't send more than 10 flights to San Diego. So basically anything below that purple line is where y is less than or equal to 10. But here's the thing, we need to consider the areas that satisfy both of these. So where is the region that satisfies both of these? Well, it's within the first quadrant, just this rectangular portion here. And if we think about that, we really have kind of these four, what I'll call extremal points. We have the point 0, 10, where we would send 0 flights to Las Vegas and 10 flights to San Diego. We have 8 flights to San Diego, or Las Vegas, and 0 flights to San Diego. And then we have the possibility of sending 8 flights to Las Vegas and 10 flights to San Diego. We can pick anything inside of this box, but already we're trying to maximize our revenue. So if we pick something that is, say, at 5, 5, well, that's only going to give us 5 flights of revenue at our $15,755 and only 5 flights on our airline that's going to make us $13,015. So it doesn't really make sense to consider anything inside the region, and certainly not 0, 0. So we're going to make the argument that we want to go out as far as we can to what we're going to call these corner points. Same thing goes along this. If I pick this point right here, well, that's where I'm making x equal to 5 and I'm making y equal to 10, which is better than 0, 10. But 5, 10 is worse than 8, 10. Because, again, we're yielding more money on each flight. And so picking anything along this line just doesn't make sense unless you pick this corner point, because that maximizes both your x and your y. And down here it doesn't make sense just because, again, on this line, the best point for the revenue function is the point 8, 8, 10. So I think we found it. We found that best revenue, but that's not all. Let's just make another assumption in this process, and let's make this more realistic bit by bit. After discussions with shareholders, it was established additionally, in other words, another constraint, that there shouldn't be more flights to San Diego than there are to Las Vegas. What should the company do to maximize its revenue? Okay, so we're building upon this. So we still want to maximize revenue equals 15,775x plus 13,015y. Subject to our same constraint so far, x still has to be less than or equal to 8. Y still has to be less than or equal to 10, but also we're saying that there shouldn't be more flights to San Diego than there are to Las Vegas. So the number of flights to San Diego should be less than or equal to the number of flights to Las Vegas. There should not be more San Diego flights. So there should be at most the same number, but potentially less. So since y is the number of San Diego flights, yes, it is y. Y has to be less than or equal to x. That ensures that the number of flights to San Diego is potentially less than the number to Las Vegas or potentially equal to the number in Las Vegas. Well, interesting. So that means I can't ever pick 10 flights to go to San Diego. Why can't that be? Well, the biggest x can be, the largest x can be is 8. But if you pick the largest value for 10, 10 is not less than or equal to 8. So I can say, well, I'll make it one smaller. Well, 9 is still not less than or equal to 8. So the largest value that will be feasible, that will make sense in this situation for y is 8 is less than or equal to 8 is a true statement. It is equal to 8. And that right there, remember, it only has to be less than or equal to, and 8 is less than or equal to 8. It is equal to it. So at this point, we still, our objective is kind of the same. We still want to get the greatest number of flights out to each of these locations as we can. And the most I can send to Las Vegas is 8, and the most I could send to San Diego is 8. So again, I'm going to say, hey, you know what? 8, 8 is the best solution because that gives me the most number of flights, and it's going to produce the largest possible revenue that I can have. And that's, again, just an intuitive argument that if we make these any smaller, we're not going to be making money, but we can't make y any bigger because now the number of flights to San Diego has to be less than or equal to the number of flights to Las Vegas. So if I make each of these variables 8, I will get a smaller revenue than we did in problem 1, but now, because of this new constraint, I'm limited even further. So that's going to be my maximum possible revenue in this case. Well, let's do this intuitively again. Let's come back here, and now let's graph y is less than or equal to x. Okay, y is less than or equal to x. If you're unsure where to shade, whether it's below or above, one way to do this is to think about the y values are equal to the x values along that line. That's just the line y equals x. Right? That's the same function I just plotted, but it only gives me the line. It doesn't shade below it. Okay, that's where y and x are the same. But if you pick anything below that, for example, this intercept right here, 5, 0, well, 0, the y component, is indeed less than the x component for that ordered pair. So that tells you shading should definitely occur below this black line. And now we can see that our feasible region is just updated. Now we really have a triangular region of valid points. Why? Well, this is the area that satisfies all three of these. There's purple shading all in this triangle. There's green shading all in this triangle, and there's black shading in that triangle. And no other region is satisfying both. Here, of course, x is bigger than 8 and y is bigger than 10. Down here, x is bigger than 8. Yeah, y is less than 10, but it does not satisfy the green constraint as well. So we have to be in this region. And once again, we'll make the argument that it doesn't make sense to pick anything inside of that region because you can always do better by going to one of the most extreme points. And you don't want to stick along the line, kind of for the same argument that we made before, like 5, 5. Well, yeah, that's a valid point, but 5, 5 is not going to get you more revenue than 8, 8 is. So we can see that 8, 8, if we plug that into our objective function, it's going to do better than any point inside here. Now I'm going to do one thing, and to make this a little bit more intuitive is let's put a table in. And the table by default will create a column that's called x1. And then what I want to calculate here is I'm going to leave it as x1 and y1. Okay, I'm going to uncheck this because I don't want it to actually, well, yeah, I'll have it plot the points. And then what I want to do is to calculate the revenue here, which will be 15,775 times x plus, and I'm going to do times x1, so that way whatever number I enter into this table here, it'll multiply it out. 13,015 times y1. And now if I enter a point here, for example, that bottom corner point, 0, 0, we see, well, that doesn't give us any revenue. If we pick this point over here, 8, 0, well, that gives us a revenue of 126,200, but if we go with 8, 8, we can see that that gets us that $230,320 at that corner right there. And we said that anything along this line, like 5, 5, is not going to do any better because the more flights we have, the higher the revenue. You can see that gets us 143,000, which is better than 8, 0, but it's not better than 8, 8. And let's pick something in here, like maybe 5, 2, a point smack dab in this, right, almost in the center there. Well, that generates a lot less, once again, because we're picking fewer flights than we possibly can, and the more flights, the more money. Okay, let's add on to this a little bit more. And now let's say, speaking with air traffic control, it was additionally agreed to allow no more than 14 new Southwest flights from this airline. What should the company do to maximize its revenue? So now we want to add this constraint that the total number of flights that we're considering here has to be less than or equal to 14. X plus Y is less than or equal to 14. We can't have more than 14 flights. So we can't stick with the solution 8, any longer, because the sum of those two is the number of flights is 16, but we can't allow more than 14 flights. So this is no longer valid. So they have to sum to 14. They can't be bigger than that. And the reason I say they have to sum to 14, they actually don't have to sum to 14, but that's the maximum total number of flights we can have is 14. And we know that more flights equals more money because each flight brings in additional revenue. And we're assuming that we can fill them. So ways in which I could do that where the Y value is less than or equal to the X value, I can't have Y be 8. I can have Y be 7, and then that would mean that X has to be bigger than or equal to X. So the 0.77 would certainly work, because here X and Y are less than 8 and 10 respectively. The Y value is equal to the X value, and if you sum them, you do get less than or equal to 14. But another way to do this is Y can be smaller than 7, and I can still get 14 flights by making this 8. And those still sum to 14, but look at what we're doing here. Instead of sending this one flight and sending it over to San Diego and making less revenue, here I'm still getting 14 flights. I'm still sending 16 to San Diego, but I'm getting one more than I do here to Las Vegas, which is going to give me this extra amount of revenue that I get for each flight in comparison to the ones to San Diego. Now, I can't go any higher than 8 on X because X has to be less than or equal to 8, so I've maxed out my X. And I don't want to go any lower on Y because the 0.8, 5, while it does satisfy all the constraints, it only gives me 13 flights, and I know that I'm going to do best if I send 14 flights. Let's go ahead and plot this in Desmos along with our other constraints. Now, of course, this will get to be potentially a little bit distracting with all these constraints, but you can see that our black triangle was our feasible region, and now the only points that live in all of these regions are this kind of like triangle with that corner chopped off. Remember, that corner was where we had 8, 8. That was the 0.88, and that's no longer a valid point. So once again, we're going to kind of make that argument that don't pick anything along the line here, because your X plus your Y will equal 17, but for example, I'm sorry, no, that won't. Here you'll have 5, 5. That's where Y is less than or equal to X. But if you go down this line, you're not getting 14 flights. If you're on this red line, then you're getting 14 flights. But to pick anything in here doesn't make much sense because of the fact that, well, first of all, there are no integer values in here, and they aren't the most extreme points. Think about the distance from the origin. That point right there is the most extreme point in terms of being what we call a corner point. So we have really 4 points to consider here. 3 if you consider that 0, 0 isn't going to do much good. 2 if you consider that 8, 0 is not going to do much good because, again, you're not using up all the flights that you can, and more flights equals more money. So down here, let's plot. We'll put in 2 more points. We'll put in the 0.86. That yields a revenue of $204,290. And if we do 7, 7, well, that's going to be less because of the fact that here we're making 13,000 $15, but only 6 times. Here we're making $13,015 7 times, but we're making $15,775 one fewer time. So we want to make as many of those flights to Las Vegas as we can, and that's going to give us $204,290. So this is going to be $204,290. There we go. So let's make this problem a little bit more exciting and say, suppose that after further research, it's indicated that Las Vegas will likely only fill an average of 110 seats. Is the best option in number 3 still the best option? Well, how does that change this problem? I mean, our constraints are still the same, but now we're not going to yield as much money on each Las Vegas flight because we're still making, I think it was $115 per passenger. Will be a $115 fee per one passenger, but now we have 110 passengers, and so that is going to give us a smaller revenue. 115 times 110 is equal to $12,650, and so notice that would modify this value over here. So as a result of that, now x matters less than y. We want to make y as big as possible, and so now that will change the conclusion. That will change our conclusion to now that Las Vegas flights yield less, maximize San Diego flights. Now the thing is, the largest that you can make a San Diego flight is 7. You can't make it 8 because y has to be less than or equal to x, and x can't go above 8. So now we would pick the point. Our optimal point would be 7.7 with a revenue of, come back here and see that for 7.7, if we changed our equation up here and we made this coefficient 12,650, notice our points right here have now shifted a little. It's a little, not a lot better, but it's a little bit better to have more San Diego flights than we did in the previous solution. So it's going to give us $179,655 instead of $179,290. And I think that was $655. Okay, so what we've just ultimately done here is we've built up a full-on linear programming problem, and oftentimes we don't develop these constraints one by one. But I like this example because I think it builds some of our intuition without having to see why we're picking the corner points. And in the next video, we'll actually make this a theorem. It's called the fundamental theorem of linear programming, which says in your feasible region, as long as it's what we call bounded, you only need to focus on your corner points. You don't actually need to focus on the entire region. So among these 4 points, regardless of what your objective function is, as long as this right here is your bounded feasible region, then one of these corner points will always maximize or minimize, well, I should say maximize and minimize an objective function. It just depends on what you're trying to do. If we were trying to minimize revenue, of course, we would have picked 0, 0, because that's the smallest point. So ultimately, we've solved a problem like this, where normally we would input all of our constraints, look at the feasible region, we would find these, in this case, 4 corner points, and we would test all 4 of them in our revenue function and see which one produces the largest possible result.